one of the applications of a partial derivative is to find the slopes of a surface. What does that mean? That means if I have some defined surface and I have a point, I can see how the surface is changing at that point for each given direction. So let's start over here. We have a function of x and y, negative x squared over 2 minus y squared over minus y squared plus 25 over 8. And at the point 1/2, 1, 2, we want to figure out what the slopes are. So what that tells me is if I were to plug in 1/2, 1, and 1/2 and 1 here, the output of the function would be 2. What it also tells me is that I need to find the partials in each direction, and then I need to evaluate them at this input point. So that's how we kind of deconstruct this problem. So let's find the partial with respect to x. Well, luckily x, y, and this constant are all split up, so the derivative is fairly straightforward. The derivative with respect to x here is negative x, and since y is held constant and this number is a constant, their derivatives their partial derivatives with respect to x are 0. So similarly, if I were to find the partial with respect to y, this is held constant, so its partial with respect to y is 0. This becomes negative 2y, and again, that's constant, so its partial with respect to anything is 0. So then if I want to find the partial at this point, I get negative 1/2, and the partial at this point is negative 2. So then those tell me that if I'm moving only in the x direction, I'm sliding downward. And if I'm moving only in the y direction, I am sliding downward as well, but I'm just actually sliding more quickly. So that's how we get these derivatives. Let's do something a little more complicated, but not terribly complicated. So let's find these slopes. So again, that's a constant, so its partial with respect to x is 0. And that only has y's and numbers, so that's a constant from a partial with respect to x. So we have this, so we have to use the power rule and chain rule stuff. So we have 2x minus 1. And then we would take the derivative of the inside, but that's just 1. Oh, I'm sorry, that's a negative 2. Forgot about that negative. So the partial with respect to y this is a constant. This doesn't have any y's in it, so it's a constant for practical purposes. And then we have this thing does have y's in it, so we have to bring down negative 2y minus 2. And then again, the chain rule would take the derivative of the inside, the derivative of y minus 2 is just 1. So then we want to plug in the points. So we have 0, so that tells me x isn't changing at all. So in that particular point, there's no change in the direction. And at that point, there's no change in direction. Now, if we go back to introductory calculus, remember when your derivative had a value of 0, it often indicated that we were at a critical point. And a critical point could relate to like a maximum or a minimum. It didn't necessarily, but it could. And it might be even related to an inflection point and things like that. But what we find is similar behavior here. And what you can actually find is you can have kind of almost like a critical point in one direction, but not in another. Think of if I had like a surface that was moving like a sine wave, but it was that cylinder style where it's like a sheet of a sine wave. You could have something that had that flat derivative, that local maximum at a top, but in for this direction, but for that direction, it was actually changing. I guess in that case it may not be, but regardless, the idea is that you could have changes in multiple directions. Let's take a look at a small little sketch of what we're dealing with here to see if we can't understand that, why this is our answer. So if you look at this problem, if this were just an x squared and this were just a y squared, what you have is a paraboloid. You'd have something that is paraboloid that opens downward because you have those negatives there. And what these values tell me is that this is that paraboloid shifted up 1 in the z direction and shifted over 1 and over 2 in the x and y directions respectively. So you have something that is kind of opens downward like a parabola, but it shifted over 1 in the x and over 2 in the y, and it shifted up 1 in the z. And it's that elliptic paraboloid kind of stuff. Anyway, what we find is this piece. One, two, one. So it's the very top end of that sort of bell. Well, at the top end of the bell, it's like a peak of a curve, except it's a peak of a surface. And at the peak of the surface, you're going to have these partials equal to 0.